Okay, guys, you have made it to your final quadrilateral in the series. In this video, we're going to talk about kites, okay? And kites are way, way, way different than a lot of the shapes that we have studied, so let's get started. All right, I've got my tools still handy. Hopefully you've got some tools too that you can follow along. So let's take a look at this kite. It says using the ruler on the centimeter side and the protractor, let's work on the kite here. I'm going to start on the side measures again. All right, let's start with AD. Yoink. I'm getting from A to D looks like 3.8. We'll go with 3.8 centimeters. Okay, come on over to AB. And we've got maybe 6.1. Okay. If you've had any trouble with your measuring tools in this unit, I really, really need to know because, guys, if you take anything with you from geometry, my gosh, hopefully you can use a ruler and a compass and a protractor to do future work, okay? Next, we've got CB down here. Hey, there's that 6.1 again. So look at that. We know we have one relationship already. And then finally, DC. I am getting that 3.8 again. So another relationship there. All right, so already I can tell something super important has happened. I can tell that BD right here is a line of symmetry. It is cutting the shape in half right across the middle. Everything on top is a match to everything below. So we've got a line of symmetry again. We can use that as much as possible, okay? All right, let's talk about the diagonals this time. Diagonal AC. Okay, AC. I'm getting like 6.3, 6.4, something in there. I'll go with 6.4. And B to D. Looks like something close to 7.3 maybe. Okay. And now for the pieces of the diagonal. Now, for so long, E was a midpoint. Take a look at E. Don't overthink it. E is kind of a midpoint, right? Like if I look at E going this way, it's certainly not a midpoint. It is not in the middle of B to D. But if I look at E going this way, it is a midpoint. It is right in the middle from A to C. So it's sort of a midpoint. We have some midpoint qualities going here. E is the midpoint of AC. It's only the midpoint of AC, not DB. Okay. All right, so if we got A to C is 6.4, then that means we should be able to take that 6.4, slice it, and find the two parts, which would be 3.2. So that would be AE is 3.2 and EC is 3.2. Let's confirm with our ruler here. From A to E, 3.2. From E to C, another 3.2. Pretty good. Nice. Okay, since E is not the midpoint going this direction, we cannot cut this number in half. We cannot cut that 7.3 in half. We're going to have to rely on something else. Now, I want to hold off a second and show you something. So we're going to come back to these two. What I want to show you is this angle measurement. AEB. Can you guess what is happening here? Eyeball it. What do you think it is? Use your protractor to confirm it if you can't see it. We've got our setup perfectly positioned. And where is this line of symmetry headed? But straight to 90 degrees. So we have a right angle in here. If we use our vertical angle, that gives us a second right angle at CED. If we use our linear pairs, that gives us two more right angles at BEC and DEA. So 4 right angles in the middle of that shape, which means if you have a right angle, you also have a right triangle. And if you have a right triangle, I hope something major is flashing in your head. If you have a right triangle, you have Pythagorean theorem. So instead of grabbing my ruler to measure BE and DE, I'm going to use the Pythagorean theorem. I'm going to use it right now on ED since that's what I've highlighted. So 3.2 can be my A squared. 3.8 is across from the right angle here, so that has to be the C, which means I'm solving for the B. Take a moment, use whatever skills you have to solve for B. That could be to finish solving, or you could go ahead and use NSolve if you'd like. All right, let's compare here. I worked my Pythagorean theorem, and I got a B value of approximately 2.05. 2.05 for ED. Whoopsie. 2.05. Now I'm putting a little star on that because I used Pythagorean theorem to get that. There's no way I could use my my ruler to get 2.05. I would have either called that 2.1 or 2.0, depending on where I set up my ruler. So there's no way I would have gotten such an accurate answer with just my ruler here. So I put a little star on that so that I would remember that. Now, if I say all the way across from B to D is 7.3, and I say I used up 2.05 for ED, okay, do a simple subtraction here, and I'll have the other piece there as 5.25. Sorry about this scribble. 5.25 centimeters for BE. Ooh, so right triangles are back. There are 3 shapes now that we could use our right triangles on. Squares, rhombus, and kites. They all meet at a perpendicular piece here in the middle. All right, let's keep working here. E to A to B. E, A, B. So we're looking at this angle. Okay, well guys, why don't we just take a second and review something else? Because we are dealing with right triangles, Pythagorean theorem's not the only thing we could do. We could also work on our SOHCAHTOA. So why not? Why not throw that in there? Sure, you could just grab your protractor and measure it, but I'm telling you that these things are going to pop up because we're at the highest level of our study here. We're mixing everything together to formalize these shapes. So let's practice some SOHCAHTOA. I think I'm going to use this, I have options. I have my opposite, hypotenuse, and adjacent. I know that I got 5.25 through a series of different things. I had to use subtraction. I had to use Pythagorean theorem. I had to use 2 previously measured things. So I think I'm going to avoid that one. I'm going to go with the most basics, which was 6.1. I just measured with my ruler, and 3.2 was pretty easy to get. So that is the adjacent to the angle I'm looking at, and the hypotenuse to the angle I'm looking at, which would be cosine. So I want to find the angle, which is the inverse cosine of the adjacent value 3.2 over the hypotenuse value 6.1. Take a minute, use your calculator, and solve for theta. All right, check it out. Using inverse cosine, I got this angle at 58.36, and that was a rounded answer. Now, we haven't been going that deep with any of our measurements, and that is because there's no way our protractor could get such an accurate answer. If I were to measure this angle with my protractor, set it up well here. Okay, gotta have my ruler to lengthen the side. I'd probably be measuring that at like 57, 50, hold on, let's see, get things set up. 58, it looks like it's hitting right at 58 degrees. So I'm going to go with 58 when I write it down, and I'll probably just use 58 to move forward. But I'm just telling you that this is a much more accurate way than just using a primitive tool like a protractor. All right, let's see what else we can do. Let's put our tools away a minute and think. Well, one thing I can do is I can find the last angle within this triangle. Let me highlight the triangle so you know which I'm talking about. I'm talking about this pink triangle here. That's the right triangle we were just working on. Well, 3 angles of a triangle have to add up to 180 degrees. So I already used up the 90 at angle E here in the middle and that 58 degree angle that we just measured, or that we just solved for. So that leaves me with 32 degrees over here at EBA. EBA, 32 degrees. Something else I can do is just transfer this down. There's my line of symmetry. So if this kite folds over, this 32 degree angle can transfer down. This 58 degree angle can transfer down. So now I've got ECB at 58 degrees and EBC at 32 degrees. So I'm getting there. I can add these two together and I've got this whole angle, 32 and 32, totals up to a total of 64 degrees. So I've got that. So I had a little bit more work to do, and it's on the piece that's not symmetric. It's on the piece that's not symmetric, okay? So let's see what else there is to do here. Now we're working on the yellow triangle. Well, I could certainly just pull out my protractor because right now I have it. But on the SOL, I'm not going to have it. I don't have a protractor. So I'm going to have to find something else to do. And it's going to be trig. I'm going to have to use trig. So I'm going to set up another SOHCAHTOA problem. Let me set things up over here. Get ready. Okay. Now, remember, we did Pythagorean theorem to get the 2.05. So I don't want to use that one. I think I want to use the 3.2 and the 3.8 that I measured, which is another cosine problem. I'm trying to find an angle measurement, which means I need the inverse of cosine. Anytime I want to find an angle, that's the inverse of cosine. Cosine calls for the adjacent length, which is 3.2, over the hypotenuse length, which is 3.8. All right, so take a minute. I'm going to pause the video, use your trig function, and solve for cosine. So, solve for the angle. All right, so how'd you do? I got theta here, which is the upper angle we're looking at, as 32.64. Guys, of course, I'm not going to get 32.64 on the protractor. Okay, I'm really trying to hammer that idea in that there's no way to get such awesome measures with a protractor. If I were to use the protractor, I would have probably rounded this to 35. or maybe even 34. Okay, so I'm definitely able to see a much better measurement with my trig. So let's see, we've rounded everything else down. Let's see, we rounded this to 58. Let's think about that. If this is 58, how much do you think should be here? What should we round that to? Whoa, let's check something out. 32.64. See, 32.64 plus 58.36. 91. So this whole angle is 91 total. So if it's 91 and I want to figure out what to write down, I wrote down 58 for the first set. I should be writing down 33 for the second set. Of course, that's also what it rounds to. So EAD, I'm going to write up as 33. And that, of course, can flip over this line of symmetry to be ECD, 33. So just a little bit left. Hang with me. We're almost done. We're working inside this yellow triangle. We've got a 33-degree angle and a 90-degree angle, one final angle. You know they have to add up to how much? Think about it. Answer my question. Say it out loud if you want to. 180 degrees. So 180, we've used 33, we've used 90, we have 57 left here at angle EDA. That 57, flip over the line of symmetry, would also be at angle EDC. And we have finished this giant puzzle. To get our final big angle here, we could just add 57 plus 57 for a total of 114 degrees. Whew. We did it. Man, look at all this great work. Pythagorean theorem, right triangles, midpoints. We've got our protractor going. We've got our ruler going. Man, if this unit doesn't make you feel like a geometry superstar, I don't know what will. If you're struggling with any piece of this at all, please come let me know, because it all works together to build such a pretty final unit here with the shapes. Now, let's take what we know about kites and let's write up our characteristics for every kite. Both pairs of opposite sides parallel. No way. Not even one pair of opposite sides parallel. A kite is so out there in the world of quadrilaterals. There are no parallel pieces, so we never talked about alternate interior. We never talked about consecutive interior. All those are out the window here. How about this one? Both pairs of opposite sides congruent. That's a no. I know we have two pairs of opposite sides congruent, or two pairs of sides that are congruent, but they're not opposite sides. So that's out. Not even one pair of opposite sides are congruent. How about both pair of opposite angles congruent? That's a big nope. We had one pair of opposite angles congruent, the 91s, but not this direction, a 114 and a 64, not congruent. All four angles congruent to each other, no way. Diagonals congruent, no way. 6.4 and 7.3. Diagonals bisect each other, not really. One of the diagonals got bisected, but not both of them. The diagonals are perpendicular to each other. And diagonals bisect the angles of the figure, sort of. It bisects this the end caps on the line of symmetry, but not the other direction. So sort of, these are sort ofs. It bisects one pair of angles, and it bisects one diagonal, but not both. Oh my goodness. Hey, look, here's a surprise for you. There are no SOL problems that go with kites. So why did she put us through this craziness? Why did Miss Denton make me do it? Because kites are so freaking cool. Kites are awesome. You've got all this upper level geometry happening to understand a kite. So thanks for joining me. Practice your IXLs on it because it's going to be an awesome spiral review to some of these other topics. Happy studying.